Hello, everyone. Welcome to another wonderful day of chemistry. So today we're really going to dive into a topic that we've brought up a couple times before, which is the idea of how we can use thermodynamic cycles, or more or less a closed energy cycle, to determine an unknown chemical reaction. So this is very much the idea we use to derive Kirchhoff's law. Now, one of the most iconic examples of this is going to be the Born-Haber cycle. This is really a good example of if I've got a very complicated process, I can break this reaction into known steps and then figure out the step I don't know. So this most iconic example is going to be the Born-Haber cycle, which is used to calculate the enthalpies of formation for an ionic solid. And this can be done by working our way through the system. So again, the enthalpies of formation is going to be going from the elements in their most stable state, so sodium and chlorine, to sodium chloride. So classic formation reaction. But trying to do this experimentally is very difficult. So instead, we go the long way around. And we know the sum of going from here to here should also be the sum of going the long way around, which involves a series of steps, such as the sublimation of sodium to sodium gas, the this bond dissociation energy for chlorine going to from chlorine diatomic chlorine gas to monatomic, and then followed by the ionization of chlorine or sodium, and then the electron affinity of sodium to take that same of chlorine to take that same electron and move it onto the chlorine. And then we have something called the lattice energy, going from independent sodium and chlorine ions into sodium chloride. So all of five of these steps can be accomplished experimentally. And so we can add these together to figure out the known system. So again, let's go ahead and take a look at this kind of in detail. So we're looking for the energy of formation of sodium plus chlorine gives us sodium chloride. Now we can go ahead and do this several ways. My favorite way is to pick a species that I'm interested in this case, sodium on the right, and I'm going to try and build up the whole rest of the reaction, canceling things as I go. So the reaction that starts with sodium is going to be the sodium sublimation. So I go from sodium solid to sodium gas. And this is an enthalpically unfavorable reaction as demonstrated by the positive enthalpy. Then we have the ionization of sodium, at which point I now eliminate this sodium gas to replace it with the sodium ion gas, generating an electron. Now we can do the same thing with the chlorine. So chlorine starts as diatomic chlorine. So we've got that right. Now, if I look at the bond dissociation enthalpy, that will be breaking it apart. But notice I'm only breaking up 1/2 of the chlorine. So I'm only going to use half that bond dissociation energy, which is about 121 kilojoules. So again, makes sense. Breaking apart a bond should be unfavorable. Then that chlorine can then gain an electron in a energetically favorable step to make the chlorine gas. So again, notice here, we can cancel out the species that cancels. And also notice here, we've now generated an electron and consumed an electron. So now what we're left is we need to cancel out the sodium ion and the chlorine ion. And I can do this using that lattice energy. So the lattice energy uses the sodium, and that cancels, and the chlorine. So notice that we've now canceled everything except for the sodium solid, the chlorine gas, and our desired product. That means since everything canceled out, I should be able to just straight up add up these energies. And when I do so, that should produce me my enthalpy of formation for sodium chloride. Adding up all these energies, we get a value of negative 411 kilojoules per mole, which is the exact value that we would expect. So again, notice this is very much similar to what we did with the temperature adjustments, just on a much grander scale. And trying to know what reactions we can pair together can often be the most difficult, which is one of the reasons we often will focus on classic examples like the Born-Haber cycle. Another good example that we kind of brought up a little bit last time is how I figure out the energies, the enthalpies, the free energies of formation for a ionic for an ion. So let's say I want to go ahead and figure out the energies of formation for dissolved proton and chlorine. So I really am going to be focusing on how I make that HCl, that aqueous HCl species, which again can be considered as the independent ions. So how can I go ahead and make that? Again, from its base components. So I'm looking at that energy of formation. So again, I'm going to have to work my way through the system. So again, one of my favorite ways, start with one of the base components. If I'm looking at the energy of formation, that means I have to start with hydrogen and I have to start with chlorine. So another good place to start is, again, starting with that hydrogen, disassociating. Then once I have that hydrogen, again, it can lose the ion. So again, we can go ahead and cancel out the hydrogen gas. So now I've got my proton, but I've got it in the wrong phase. So the next step I'm going to have to do the solution. But we'll first do the same thing with the chlorine. We start with chlorine, its most stable phase, which is the diatomic. So I'm also going to have to use the bond dissociation. Notice in both cases, I'm using 1/2. And then again, instead of the ionization, losing an electron, I've got electron affinity. So again, that does change the sign of the process. But notice now I can not only cancel out the chlorine, but I also need to cancel out that electron. So now we're left with proton and chlorine, but again, in the wrong phase. So we're going to find the solution for both components. So the solution energy for the chlorine and the solution energy for the proton. So we can go ahead and cancel both out. And now, again, I'm going from energy formation for the proton to both of the aqueous species, or I've got my full energy formation reaction, which again, I can determine. But it turns out, and again, we can look up the energy of formation for this process and notice the whole cycle adds up. Now, this is necessarily generally what we did for the sodium chloride solid case. But sometimes it turns out we're missing a step along the way. In this case, I do know the energy of formation for my HCl. But what I really need to figure out is the solvation energy for the chloride ion. This can actually be difficult to determine. The proton is relatively commonly used, so we do know that. So if we know all the other energies, we can rearrange this process to solve for the one we know. So in this case, we can rearrange and we can find the solvation energy from the chlorine by adding up the negative of everybody except for that formation reaction and adding them all together. Now, when I do this, we find out that the energy of solvation for the chlorine is -60 kilojoules, meaning that, hey, indeed, it's very favorable for a chlorine to go from the gas phase to the aqueous phase. Makes sense. So that kind of brings us to our summary of thermodynamic cycles. This is more of a skill than trying to memorize the exact case. So just make sure if you know a series of reactions, you can go ahead and do the arithmetic to rearrange everything to solve for the component you know. So next time, we're going to dive back into our knowledge of our major four thermodynamic state functions and um, internal energy, enthalpy, Helmholtz, and Gibbs free energies. And we're going to figure out how can I go ahead and determine these with fewer approximations. Next time, it's the fundamental equation of thermodynamics. Until then, take care.